Hey everyone. I've gotten a few questions about the process of splitting our data into training, test, and safe data. Um, since that's the case, I wanted to make a video just discussing first, why do we split our data? What's the point? And then second, how does train test split work? And what are the outputs of that function? And so I hope that this video helps to kind of alleviate some of the questions you still have. So what I'm going to do is run through this notebook with you. The code here is not important at all. So don't pay attention to any of the code. What I want you to do is look at the pictures and talk with me through the numbers that we're seeing. I'm importing some libraries just to get the notebook to run. I'm going to generate some fake data. And we're going to try to build a model to fit this fake data. I generate the data, and here it is. We want to build a linear regression model to fit this data. Now, the data that we're trying to fit is pretty small. It's only 8 points. What I'm going to do is I'm going to fit and plot 5 separate models. I'm going to plot a straight line model, a model that allows a little bit of curvature, all the way through a 6th order model that allows a lot of curvature. So basically, a straight line, a quadratic, a cubic, a 4th degree, a 5th degree, and a 6th degree model. Increasing the degree increases the amount of curvature that the model is allowed to have. And increased curvature, what we've used as a term to describe increased curvature is increasing flexibility. Increasing the flexibility of a model increases its ability to fit the training data. So what we should see is the more curvy the model, the better the fit. And so here are our models. So we start in the top left with the straight line model fitting our training data or our data. We haven't split anything into training or test data here. So our model fits our data. Then we have a quadratic model that allows a little bit of curvature, a cubic model allowing a little bit more, a 4th degree model, a 5th degree model, and a 6th degree model. And you can see what's happening. Again, as the flexibility of the model increases, that improves the ability of the model to fit the training data really well. This straight line model captures a general trend, but it doesn't go through all of our data points. While the 6th degree model captures a really specific relationship between the data points. It essentially crosses through all of them. At this point, we'd like to assess our models. I'm going to assess the models using root mean squared error because that's the most common error metric, and it's the one that we're going to use throughout our course. And what we'll see is a confirmation of what we saw with our eyes. The straight line model has a root mean squared error of 229. We allow a little bit of curvature, that root mean squared error drops. And as we increase the flexibility of our model, we continue to see a drop in the root mean squared error. So according to these metrics, it seems like the 6th order model, the 6th degree model with a lot of curvature, is in fact the best model. And we're continuing to see improvement, so that might entice us to build a 7th degree model, an 8th degree model, a 9th degree model, and continue increasing the flexibility. Remember what these models are used for, though. These models are used to predict future data. So let's see how these models will perform on future data. What I'm going to do is I'm going to generate some brand new data. That brand new data follows exactly the same trend as our original data did. So now we're generating data from the future, and here are our models, still in blue. You can see the faded out training data points. They're the blue circles. And now our triangular data points are our new data. Now, visually, we can see that the fit is a little bit worse in all of the cases. What we'll do is we'll compute the root mean squared error on our new data and check this out. The root mean squared error on the straight line model is 281. The root mean squared error on the quadratic model now goes up to 293. And if you look at what happens as we increase the flexibility of these models, the error metric gets worse. And what was our best model is now by far our worst model. So where we did expect with the training we did to have an error metric of around 61. So on average, we'd expect our predictions to be off by about 61 units. Well, in reality, when the model's applied in the future, we're off by over 4,500. That's terrible. And we need a way to protect against this. So how do we do it? The answer is train test split. So what we should have done at first is we should have taken our data and split it into at least 2 piles. In our class, we're splitting it into 3 piles so that we have an intermediate pile to allow models to be tested against one another. And then we can have this safe set off to the side that we're just doing one last check on with our final model. But let's just explore train test split here. What I'm going to do is I'm going to generate some new random data. I'm going to generate a bit more this time, so 100 data points. But this data is still coming from the same population as our previously generated data does. You can check and see that the way I'm generating X is exactly the same, just the number of data points I'm generating is different. And the way I'm generating Y as it relates to X is exactly the same as well. So nothing here is changing. What I'm going to do next is I'm going to take this data and I'm going to split it up using train test split. Now, train test split is kind of a mysterious function because we just call it on some objects and then we get 4 different outputs. But what's really happening? And so what I'm going to do is I'm going to draw on the screen here to kind of hopefully explain to you what the deal is. So with train test split, what we have here is we have a data frame of input features. So there's our input features. Here, what we've done is we have a column for X, a column for X squared, X cubed, all the way off until we get to this last column that's for X to the 6th. This is what's allowing us to build that first order straight line model all the way through the model that includes all of these features, the 6th degree model. Next to that, we have the response values. So that's Y, those are our responses. And I guess I should do it this way to be consistent. So the response values here, they're Y. What we're doing now is we're putting those things into train test split. And now what train test split is going to do is it's randomly going to select rows to split them between a training data set and a test data set. So here's the way this works. I'm going to shuffle up all of my rows. Once they're shuffled, I'm going to take the way we've set this up, 80% of those rows and move them into the training data. So we're going to shuffle these up. At the same time we're shuffling the rows in the features data frame, we're shuffling the rows in the response data frame, and we're shuffling them the exact same way. So maybe a better picture here might be that we're kind of gluing these things together. And as the input features get shuffled, the response vector gets shuffled the same exact way. Once that's done, what we're going to do is we're going to take the top 80% of rows. Again, where the 80% is coming from here, we can define this to be anything we want. All of that is going to be moved over into an object called xtrain, where we've defined that name here. There's nothing special about the name. Python won't complain about it. And the corresponding entries from the response vector are going to go into ytrain. And now the remaining rows, so those bottom 20% of rows from the input features, those are going to get moved into a new object called xtest. And the corresponding entries in the response column, those are moving into ytest. So now you can see that we have 4 objects coming out of the function: xtrain, xtest, ytrain, and ytest. And those are these 4 objects out here. So what did train test split do? It took our input features, we called them features df, and it took our response column, it glued those things together so that everything stayed lined up. Then it shuffled all of the rows. Once it was done shuffling, it broke off a training set of the appropriate size where we defined what that size would be. Here we chose 80%. So I get the proportion of the input features that should belong to the training data. That's what we're labeling here as xtrain. The proportion of the response variables that should belong to the training data, that's ytrain. That's what was here. Then I get the remaining set, a subset for the input features, that's xtest. And the remaining subset of the response column, which is going to be ytest. And so I get 4 objects out of train test split. And so that's how train test split is working. It gives us 4 objects where 2 of the objects correspond to the training data, 2 of the objects correspond to the test data. So how does that help? Well, remember we saw in the first 2 examples that when the model knew the answers ahead of time, increasing flexibility led to improved fit. That improved fit, though, on the training data didn't necessarily lead to better fit on new data as it comes in. So we needed some way to kind of mimic the idea that we're going to apply our model to new data, but we don't want to wait until new data comes in order to figure out, did we make the right choice about which model was best or not? And so what we've done now is we've taken our data and split it up into 2 pieces: the training data, which we're going to feed to the model. The model will be able to see all of that information. And the test data, which we're going to move to the side and we're going to hide it from our model. That's going to play the role of the brand new data. And so let's see what ends up happening. We're not going to draw any pictures this time. All I'm going to do is I'm going to fit the models on the training data that we have now. And then we're going to assess the models on both the training data, getting a training error metric, as well as on the hidden test data. So the model doesn't know the answers in the case of the test data. Remember that. And so now we can see with the training data, increased flexibility leads to increased fit. All of these root mean squared error metrics are decreasing. Again, we end up with training error suggesting that the most flexible model, the 6-degree model, is the best model. But we're not going to be tricked this time, because we're going to apply our models to unseen data. It's not data that comes from the future. We don't have that ability, but it's data that we hid. We kept it back from the model. And when our model didn't know the answers, well, we can see that increased flexibility is actually leading to worse fit for the most part. We get an improvement with the 6-degree model over the 5th-degree model, but none of those models beat the straight line model. And so we weren't tricked this time. Test error shows us what the most appropriate model is. And that's the importance of splitting your data into seen training data and unseen data like the test and safe sets. I hope you found this helpful. please reach back out with any questions you have. Thanks, everyone.